area using an infinite number of rectangles, right? So while I'm thinking about it, anybody need that handout from last time? The one with the blue area in it. Blue areas. Anybody else see that? Okay. Yeah, and I want to look at this too. So we'll use that. So let's start off with that one problem. Then I'll see if you guys have any other homework questions. This one problem, it's in section 5.1. They have an example of it, and example 4 is an example of it. Section 5.1. Let's see if I left this guy on. Oh, poor little dude. One point, my poor Celtics, 1 point. I don't get ESPN either site. I don't do cable. Cable's stupid, except for that you don't get sports if you don't do cable. Oh, I'll be right. Sorry. What's this going to do with your class? You have nothing, I'm sorry. Okay. Alright. It wasn't this exact problem, it was this one. That's for homework, right? So they give you 12 seconds time interval, right? So 0 seconds, 12 seconds, so estimated distance traveled by the motorcycle during this time. So why does it make sense that if I integrate this, or if I find the area, I'll just keep saying it like that, I find the area under this curve, it's going to end up being in what units? Feet, because it's going to be the y-axis variable times the x-axis variable. Finding the area, so doing the height times the width. 11. So it's going to be a position. It's going to actually be a distance traveled. Now, something I haven't talked about, since this seems to be a good place to talk about it. Stabilize. Stop. Okay. I haven't said this yet. I can't remember if it comes up in the homework yet, but everything we've looked at so far, it's been something like this here with a function. It's and then I get an area. But what happens when this happens? If I'm going from A to B, what happens back here? It's a negative area, that's all. Don't freak out. It's just a negative area. Kind of makes sense. So if you think about it in the standpoint of velocity versus time, here I'm going away from you, and then here I'm coming back. So it makes sense that I should subtract that off from how far I made it away from you. Do you guys get that? Do you guys get that? Are you okay with the fact that calculus, we're starting to go, okay, area can be negative. Why not? It actually just means I'm subtracting this amount off. If I actually wanted the total distance I've gone, then I want to find this area and find that the opposite of that area and then add them together. Does that make sense? It's sort of like what we had to do back when we did that funky thing where I had to figure out the total distance you went. Well, if I go over here and then I come right back, it's not 0, I've just gone somewhere, didn't I? I've gone some distance away and back, so I got to add them together. I got to absolute value it or whatever. You guys get me? So this idea of negative area existing is neat. And it's not truly negative area, it's just that this area is negative because I want to subtract it. Because I'm losing that much whatever. Okay, maybe. Okay. Some of you guys are giving me some kind of sign that you understand. Alright. So this problem is nowhere near as hard as it might sound at first. The one thing you got to be careful about is, it's not a bad idea to graph this. It's just that when you graph this, Not screwing. Just trust me, it's a graph. When you graph these points, you don't know how to connect them. Is it connected like this? Is it connected like that? Is it connected straight across? So if you do graph it, you just assume you just connect them with lines because that's all you know. That's all you know. You don't know what it looks like in the middle. So what I'm saying is you can't graphically determine if it's an overestimate or an underestimate because I don't know what my function's doing between the points. But drawing a graph, a real quick little sketch of it's not a bad idea because then it kind of grounds you with your rectangles, right? So when they say using the first, at the beginning of the time interval, what's the first time interval? Interval implies two sides, 0 to 12. So if I'm using the beginning, I'm going to use the output at 0. And then for the next rectangle, I'm going to use the output at 12. And my last rectangle is going to be, its height is going to be determined by what? So that's out here at 48 to 60. So how tall is it going to be if I'm using the beginning of the time intervals? It's going to be dependent on that. So is the output of that going to be used at all? No. You understand what I'm saying? So what is the width of each time interval? Oh, I might as well turn you around. I really do need to hire somebody. So what's the width of my time intervals? 12. So now I just need to do the sum of my f delta x. So I can do 12 times f is 0, 30 plus 28, and then you stop at 24. I know, before I put 48, I'm with you. So which way you want to say it? I don't know. And then the next one is going to be using the velocities at the end. So you're going to start at 28 and go all the way down to 27. So it will be a little bit different. So one is going to be an overestimate. One's going to be an under. How can you tell which one's bigger? Bless you. To be honest, they could both be underestimates. It's a little weird. Why? How could they? Because again, I don't know what's going on in the middle. Maybe in the middle is like, wah, wah. There's nothing that says it couldn't be. Like I know somebody's recording my speed every 12 seconds, so every 12 seconds I slow down and they go, yeah, oh shit. Yeah, oh shit. Right? I don't know if you're saying that or what. I don't know. This is besides the point a little bit, but the idea of over and underestimate kind of goes out the window, to be honest. So their part C is kind of funny. I think they want you to say who's bigger is the over, but that's not really true. They could both be underestimates. They could both be overestimates. What's most likely is the bigger one is an overestimate, but you don't know for sure. So that's how you can answer that question. You just say, I don't know, because I don't know what it's doing in between the points. Yay! Alright, so that one is in some of your futures. And some of you who tried to do it before now maybe know how to do it better. So before you launch into the next level, any specific questions from homework? Yeah. And that 5-1, right?
Yeah.
Oh, good. All right. 19. And don't. It's obvious you shouldn't feel bad about this because I don't know if your next question is going to be in the next section because normally 19 is the easier part compared to like number 22, but they're both difficult. So you know.
Yeah, I have a question.
I had a feeling. And not just you either. Every damn person in here, if they've tried it, should have a question about it. So this is a good place to look at this handout I gave you. There. Oh, jeez. I'm going to turn this thing again. No, it's good. So here. Let me just copy this photo. These are the steps for beginning the process of rewriting something into the summation form, right? Blah, 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 blah. And in fact, this is a little evil to have this in section 5.1. Did they talk about it? Yeah, good, okay. Definition 2, it does talk about it. So here, without the limit, because the limit idea is sort of like section 5.2. Section 5.1 stops at add up all the triangles. Add up all the rectangles, right? The width of the rectangle, the height of the rectangle. You get areas of rectangles, so then I want to add them up. right? I equals 1, 2, whatever. So all this question is asking you is, take the function they give you. So they give you this function here. What was x? 2x. And it goes from 1 to 3. And then put it in this form. So I know this handout is for section 5.2, but the first couple steps are 5.1 really, the end of 5.1. So I need to first figure out my width. Because what am I putting into my function? That last problem we did, why did you guys tell me it was 30 plus 27 plus whatever the hell it was? Because those were the outputs, right? But what was I actually putting into them? 0, 12. That was the output for 12. The output for 24. And how far apart are 0, 12, 24? 12 apart. So the width, if I start at A, the width tells me what the next thing is. X1, so this would be delta X away. I like it. So if I figure out what delta X is, it tells me how to write xi, and why do I need to know that? Because I need f of xi in here. Shit. I really want every step to kind of make sense why you have to do it. So you can memorize it, sure, great, fantastic, but it's so much better if you just go, well, of course I'm going to do this because it only makes sense. I'm going to give you this, by the way, with a limit on it, just like on the practice test. So it's a little prompt. What do I need to do this? I need to know what this is. And how do I know what that is? Oh shit, I need to know what that is. I mean, that's going to prompt you. So how do I figure out that width? It's the first thing I find because it's what controls everything else. It controls what I'm plugging into the function. The next thing, the next thing. And what is B and A?
3.
Yeah, so 3 minus 1 over the number of rectangles. N. I like it. And then you write what xi is. So now that I know what delta x is, 2 over n. What the hell is xi? Well, where do I start? Where's the beginning of my interval? 1. And then I want to add a width onto that. And then it's got to represent every possible input. So then to get to this one, how many widths would I add? 2. And to get to the next one, I add 3. So it only makes sense. xi... X1 would add 1. X2 would add 2. It's crazy. That's why I shows up. A plus I of those. Please let that make sense. I goes 1, 2, 3. So if I add 1 width, 2 widths, 3 widths, I collect all of my inputs that I want to use. Yes, sir?
So...
I can do that. That I can do. So what is xi? 1 plus 2i over n. That's crazy.
So that gives you the value of x, and then that you plug it in the function.
Beautiful. And now, so that sets up what my inputs are. Those are my inputs, so then I input them. Right? So the function they gave us is this. So everywhere you see an x, you're going to replace it with that thing. So thank the gods that for a couple reasons. That this is not a problem where you actually have to work it. The minute you plug that in and plug this in to the right places, you're done because it's really actually impossible for us to do this function by hand. They just want to say, make sure you can set the form up. So I really want this to make sense. We have all this stuff. Remember, we're talking about sum of I squared. Remember, we talked about that yesterday. It's on the handout, what those are. So if I can have a function where I can simplify it and get those to show up, I can actually do something with it. So every function that I can't get these, the ones that we know to show up, if it's something else, like sum of I to the 10th, or sum of 1 over I cubed, I am screwed. I can't do that by hand. Do you kind of follow? And remember when we did derivatives, weren't there some derivatives that when we set this up, I don't know if you guys remember, when we set this up, we could not evaluate this stuff. There would be no way. There are functions that I cannot do that for. So this is the idea behind every derivative, but we learned shortcuts based on what we could do to kind of build into other functions. Are you guys, that's what we did. You actually lived through that. So that's basically what we're going to do with this. We're going to do a few that we can do with this and say this is the idea behind every integral, behind every finding the area under a curve. And then we're going to try to make a connection with the antiderivative so that I can do any area that I can anti-differentiate, right? Because I can't do this for much of anything, to be honest. Just certain ones that we make that'll work. Yes, sir.
So I is always your starting value?
No, I is how do I say this?
Like for the summation notation, we have it under the E.
Oh, here. I'm sorry. Okay.
Yeah.
When you said that, I was thinking like A is the beginning.
Yeah.
But yeah, I is not. When I is 1, then you're starting. But then I is everything from 1 to n. I takes on every value.
So if the interval was like 6 to 9, then I would be 6.
No. All right. Now I see the connection. Okay. Unfortunately, on this problem, this interval started at 1.
Yeah.
If this interval was 2 to 5, let's say, what would change? It's maybe not the best way to do this, but I'm going to do it. If this was 2 to 5 instead, why would I say 5? Let's say 2 to 4. I want to make sure. The delta x would stay exactly the same, wouldn't it? Because it would be 4 minus 2. Delta x is the same, right? xi would change for one reason only.
Maybe 2.
Yeah. Right? And this would stay exactly the frickin' same because think of I as collecting all your rectangles. So what's the first rectangle we want to use? Well, rectangle number 1.
Oh, okay.
Beautiful, I like it. And then the second one is rectangle number 2. And then up to what? Up to rectangle n. Right? I like it. Which we're not telling this, oh yeah, we're letting it go to infinity. We don't want this guy to know that because this guy would freak out. It's not quite technically right, but it's actually the reality of it. I can't officially do an infinite sum. I've got to use this to say, get an expression for this in n, and then we'll let it go to infinity. Because that's the we got to say, oh shit, let's pretend it's not there, and then we'll let n go to infinity so this guy doesn't freak out. I didn't really need to say all that, but that's the way I look at it. How do you feel about that? We're going to do a whole problem like this. All the way. This one you can't finish. Once you plug all the stuff in, you're done. Don't even try to do anything because it'll freak you out. Number 22 is harder because number 22 does this in reverse. Unfreeze. Unfreeze. Okay. But I really want you to see, let's see, well, this is not the best example. If you look at the handout, I think it'll make more sense. Here. If you look at all the work that went into making this, Jeff. Oh my gosh. All right. All this work that goes into making this. Like, why is that an 8, for example, on this problem? I don't remember why. Oh, yeah, it's too far to go. Why is that a 2? There it is. This xi, why is that a 2? Because I started 2. I like it. So, look in here. Why is that a 5? Because you started. So, you can kind of pull it apart. That's your delta x. That's going to be what? What does that look like? Yeah, it's your xi. That inside is your xi. So you know what f of x is to begin with. What's f of x? What did I plug 5 plus 2i over n in?
X to the 10th.
X to the 10th. You know what f of x is. So really what they're asking you when they say, now one thing you got to realize, when they ask you what's the region, you all missed that, sorry. When they ask you what's the region, here's how a region is defined. If I want to define a region, we say it this way. I could say, that's a region, right? Isn't that a region? That's a region. And that would be very boring, because what's the height? It would be constant, f of x, right? So in general, a region is any funky-ass function and an interval. So when that problem before gave me this, that together is a region. How far do I go and how far up do I go? That's a region, from here to here and from there to there. That's a region. You with me? So on the next problem, when they say determine a region, read that as saying determine the function and the interval. That's a region. I like it. So they are exact opposites. What this guy gives you to begin with is what you need to end up with here. That's when you know you're done, when you can write this kind of thing for this. Okay, cool. I like those problems, because if you can do it backwards and forwards, you understand the parts that go into it. Okay, cool. Any other questions? Those questions, if nobody asked those questions, I would be very worried. Your lack of math would worry me. So anything else from homework before we get into a full-fledged problem from 5.2? Anything? Okay. Oh, holy crap. Yes.
For that problem, would you plug in the xi to the region equation? Or
You plug in this xi, and what's the thing say that I'll need to do with it? And it says I need to plug it into f. So everywhere you see an x, you're going to plug in that expression. It's not supposed to be nice. And why do you not care that it's not nice?
Because you're not doing it.
I don't have to do anything with it. Once I write it down, I'm done with it. Right? For this problem. Yes?
Could you do 22 from 5.2?
That's what we were just talking about. Let's see.
5.2.
Oh, I hate when they do this kind of thing. That's evil. Alright, 5.2. Oh, so, okay. Why don't we do, let's see. I like it. What did I assign you 22 and 25? Yes?
Yes.
Good. All right. So I won't mind doing 22 then. Let's do that problem as our example of a full-fledged problem.
Okay.
Cool. All right. Casey's like, yeah. Before we do a full-fledged problem, I do want to look at this handout in a couple ways. Like that, like that. No. But I'm fine. One thing I love about this problem specifically is the function is relatively simple. So if I graph it, I could actually use basic geometry to answer the question and check if calculus works. Basic geometry we know and believe in. Calculus you guys are new to, so you're like, I don't know if I believe in this shit, Jeff. And I'm like, I understand. Alright, so this is a nice kind of structure to follow when you're doing your section 5.2 homework. That's the main reason I gave this to you. And hopefully you can kind of see this is sort of similar to what we did the other day. We didn't quite get done with that one problem we were working on the board, but this is the same idea. You keep working it down until you get something based on this, and then you can replace it with what it is. Bam. Sum of I is bam, and then you can apply the limit. Alright, so obviously you got to do problem. Well, right now what I want to do is, can you take a minute and draw the region that this is describing? Just draw the region this is describing. Hopefully you understand this is not it. Right? That's not a line. This is just a general arbitrary function. Draw the region that this describes. Okay, should not take too long. Doesn't have to be anything fantastically beautiful. Normally I'm all about scale and all that shit, but this is just a rough sketch. So it goes from 2 to 5. And what's f of 2? 8. And what's f of 5? 20. So this is what it looks like. This is the area that I'm talking about right here. All right, let me stop there for a second. This is the thing to realize. Calculus is powerful. It'll do things geometry can't do directly. But when the when the function I'm doing the calculus on is a nice geometrical object that I know, then I can just use that formula for that. What shape is that in? Trapezoid. Kick ass. Why is it trapezoid? Because two sides are parallel. Only two. Exactly two sides are parallel. I like it. Who remembers what the... Well, let's identify some stuff. How tall is that? That's crazy. How tall is that? That's crazy. And how tall is that? 3. I like it. Do I care about this? Actually, I don't. Because what's the area formula for a trapezoid?
Base 1 plus base 2 over 2.
Yeah, exactly. It's just like 1/2 base times height, except how many bases are there? So you put them both in there. I mean, that's the way I remember it, right? Good old decapitated triangle, lost its head somewhere. Shot. That was morbid, I don't care. Yeah, so if you plug stuff in, what's the height? Well, it's kind of laying on the side. So the height is 3. And the sum of the bases is 28. Half of 28 is 14. 14 times 3 is 42. Which is, of course, which is what you get after doing all this stuff. Of course it is. Why? Because this stuff gets the area, and geometry gets the area, right? So geometry's like, I'm not impressed. But the calculus says, deal with this shit. And geometry, oh shit, that's you. Yeah.
Just easy functions.
Yeah, when the functions are linear for the most part, or it depends. If you have a circular function, we have geometry can tackle it. Anything that can be realized is in the shape of objects that we know area formulas for.
What
Right?
about if I divide like piece by piece and like just sum?
Sure, of course. If you could cut something up, so if I had a semicircle that was sitting up here, then it would be the semicircle plus the rectangle beneath it. That would be what the area would be. Do you see that? So I can get, geometrically, I can get that area plus that area. That's the answer, right? We don't need calculus. Poor little calculus. But how often does this happen in real life? Not very. Normally, it's just some arbitrary function up there, and calculus says, geometry can't do that shit. Okay. Do you guys with me? Because it is just finding areas. So, of course, if it ends up being a shape, we know. I could just use the area formula, and it's got to agree. Because they both do the same work. They both find the area. Just the calculus is more generally powerful. You can handle any shape. I like it. Okay. So that's one thing I want to point out. Now let's do that problem. Casey had a question on, which one was that again? 22. Alright, so this problem, let's see. So this is one that calculus has to handle. Geometry can't do it. So let's see. 22. So it's
Can I ask you,
sure.
just to make sure, this sign means infinity, right? And approach infinity.
Where?
This one, like S?
No. Well, this S, actually, they picked the letter S and elongated it to represent the infinite sum. So that S represents this whole thing.
Okay.
This becomes this. Well, elongated. I like it. Doesn't that make sense? It's almost like, holy shit, they picked something that makes sense. It's an infinite sum. It's like a big sum. Let's make a big S. Yeah. So it worked out. All right. This is exactly how the conversation went down. They have videotape. Let's see. All right, so use blah, blah, blah. All right. So the steps on that handout, obviously you're not going to be able to use the handout on the test. So what you need to do is try to get the steps to make sense. So then you can remember them easier. I'm going to give you this. I'm going to, just like in the practice, I'm going to give you this. So the prompt is that creates that, and that gets put into that. I mean, that's the process. That's why the first step is what's delta x and what's xi, and the second step is, okay, plug that into your function. And then put that together. Third step is now do all the work, right? That was just to get it set up. So my step 1, delta x.
4 minus 1.
Yeah, yes. How far I've got to go? 4 minus 1. Divided by how many rectangles I want to use? N. And do you see why? Right there, if I didn't use this limit of n and putting an n there, this would freak out. Because that would try to be 3 over infinity. That's what I meant earlier by, so it won't freak out, we keep them separate. Do everything with n, and then let n go to infinity, or everything's going to freak out in the middle. I like it. Alright, maybe. If somebody try to do it quicker in this, I know it's not going to. Now that I got delta x, what can I write an expression for?
xi.
Xi.
So a plus delta xi.
Yep. So a here is what?
A is 1.
Unfortunately, it happens to be 1 again. But we're beyond that, right? It could be anything. It's only going to change the delta and the xi. It's not going to change anything else. So xi would be 1 plus 3i over n. And to connect this with the concrete stuff we've done, this would be like going from 1 to 5, like that problem we did the other day, like that. And we put a 1 in f of 1, and then we put, I can't remember what the next one was, but did we add delta x to figure out what the next thing was to put into the function? That's exactly what this is. This is figuring out all my inputs,